Hi everyone, welcome to today's lecture about applications. This is the last lecture of our course Mathematics for Intelligent Systems, and we will have three parts, or we will have three small topics that we talk about, three different applications where we apply math in our work here in the Machine Learning and Robotics Lab. And then that's the first half of the lecture. In the second half, there will be a Q&A session. So you will be able to ask questions about the whole lecture content and the whole exercises. And we will go over it again and try to help you as much as possible. So we will start with the first application, which would be deep learning. And here we will do some quick introduction to deep learning. The slides are by my colleague Yannick Hager, who unfortunately is not able to do it today, so I will do it instead. Yeah, what is deep learning? So deep learning is a machine learning technique, and for machine learning, you probably all have heard this term already. We already had mentioned it several times in our lecture as well. And the goal is that we approximate a function, some function f star of x. And yeah, this is done, or what we will focus on here in this small introduction is supervised learning. So we assume we have a data set where we have some example data points of what the outcome should be. So we have an example of an input x, and we have multiple examples of inputs and corresponding outputs, and we want to learn the methods in here. And instead of doing it traditionally, like coming up with some own functions, own features and things, we want this to be like end-to-end and learn it. Yeah. So what we need to, or what we have in machine learning then is a function f, and we parameterize it by some set of parameters theta. And we want to learn the best function representation given the data that we have. So yeah, I will first here talk a bit about general typical neural network models. So we will look into fully connected neural networks. And after that, we will look into convolutional neural networks. So yeah, feed-forward neural network, or also called fully connected neural network, is just a very basic equation. And yeah, so we have a matrix W, we have X, so X is our input, and we have the bias vector B. And yeah, you will see this is just some linear mapping, as we have seen in the lecture before. And now what is done, so like this now computes like some new vector here. We have just simple matrix multiplication and vector addition. That's one layer. Then what is typically done is that we have multiple layers. And for deep learning, we will have, so deep would mean that we have like a lot of different layers that we stack. And then here, what's new is this sigma, which is an activation function. I will talk a bit later about possible activations function we could have here. And this in the parentheses is just the output of our previous function. So yeah, we just concatenate the functions here. And yeah, we can, as I said, we can do this multiple times for many layers, and typically in deep learning, we will have a lot of layers. So the parameters theta are just all our W's, all our parameter, all the matrices, and all the bias vectors. And we remember these zetas are what we want to learn. Like by changing these parameters, we change the function and we change the output of the function in the end. Yeah. So yeah, I already basically talked about this. We have our input is our x0 that comes into the first layer, and then we compute like the next layers by chaining together the functions. We have an activation function, and in the end, we will have an output. And yeah, this is a way of depicting this. You typically see like images like this. If you look into neural networks, you have some input here, and then you have like different layers in the middle, which are called like hidden layers because they're in the middle and are hidden from the user typically. So activation functions need to be nonlinear because if it would be linear, then a linear mapping, then you just would have, in the end, you would just have some concatenation of the two linear functions, and then you will just get out one linear function again. So we will have nonlinear activation functions in between the layers. And their typical choices are like, for example, the ReLU function, which is just the maximum of 0 and z, which is depicted here. You could improve this a bit by making it like this, so that you also have a gradient in the parts in the negative part, which sometimes performs better. Or there also are other possibilities, like a sigmoid function is very often used here, or the tanh function. Then, of course, we want to learn something, and this means we need some way of measuring the performance of the network, and this is where where a loss function comes in. So as I said, we have examples of data points with input-output pairs, and now what typically is done, we put the input pair, the input vector in our neural network, and then in the end, we will get some function out. We have this function. We have parameters for the function, which are initialized randomly, and in the end, we get some values out. And then on this output, we either do, we want to apply some loss to see how far is this output from our data point, from the label in the data point. And for regression, one could use squared error loss for classification, the log likelihood or the hinge loss, as it's typically done. So neural networks have a lot of parameters. And of course, this could also overfit a lot to the training data. So what this means is that the prediction of the neural network would perform really well on the data that we have trained on, but would not perform well on unseen data. And that's not good, because in the end, we want to perform good on the unseen data. And to prevent overfitting, there are regularization techniques which can be done. And here, just to name a few of them, there's like typical L2 or L1 regularization, like you could also do in linear regression. There's dropout. You randomly deactivate neurons, and this way you simulate like training multiple networks at once, because you have like some neurons are not working, are deactivated sometimes, and this is done randomly. You can do data augmentation, so a good way to increase performance usually is by putting more data in. If you don't have more data, you can do data augmentation, like modify your data, rotating images, flipping images. And another way to regularize neural networks is early stopping of the training procedure. So instead of training till the end, like till we end up in maybe some local minimum, we stop earlier. Yeah, so how is neural network training done? Typically, we initialize the parameters like the weight matrices and the vectors, the bias vectors, randomly. Then we can do a forward propagation where we put the inputs through the network. Then we compute the prediction error by comparing the output with the label that corresponds to the input. And then we propagate the error backwards through the network and iteratively compute gradients, which is called backpropagation, and which is a general part of neural network training. And yeah, you have seen in previous week's lecture how gradients can be computed for such functions. Then we update the parameters. Usually there's stochastic gradient descent used. So I don't know whether we have talked about this already, but yeah, gradient descent you should know from previous lectures. Stochastic just means here that we use a stochastic subset, a batch of the input data, and compute and you just do gradient descent of a subset of the data, and then we repeat this multiple times until convergence or until a maximum iteration count is reached, or we don't have any more computation time or don't want to spend more computation power. So that was typical or standard neural networks with only fully connected layers. As I already mentioned, for deep learning, you would stack multiple fully connected layers on each other. And yeah, the depth of the network is then the number of layers. I think usually one considers deep learning if you have more than 3 layers, but nowadays, like, networks can become like really deep with yeah, way more layers. And the idea of stacking these layers is that hierarchically, like, features can be learned that before needed to be designed by hand. Deep learning needs more computational power and needs more data sets. And this is or this is the main reason why, yeah, but why it is so successful, because nowadays we have like lots of computational power and we can capture lots of data, and deep learning performs super well on with large data sets, and but needs computational power, of course. So one problem of deep learning is the high number of parameters, which of course leads to, like, yeah, very complex computations. Like you have really big gradients that you need to apply, and yeah, you need a lot of computational power. If you now look into images, we will find that we have some grid structure. So we have pixels that are aligned in a grid. And if we now want to use deep learning or on this, and we put all the pixels in one vector and put it into a fully connected layer, this might not be the best idea, because we would like to use the structure of the data. We would use this grid-like structure, and we would like to use this neighborhood information that is included in the images, because typically, like, neighboring pixels correspond to the same object or to the same parts of the objects and might be kind of similar. And this is where where convolutions are helpful. Yeah, in tasks on images, there are multiple tasks, a lot of tasks possible. Typical ones are classification, where we want to detect what object is or what animal in this case is in an image. Then one could also want to do localization, like where in the image is the animal. And of course, one could also do this for like multiple animals, multiple objects. But there are way more tasks that are possible. So convolution, so in German, convolution means Faltung, which is mathematical operator. You might have heard about this. And convolutional neural networks usually is just a small filter, a square filter that are moved over the image. And you have a smaller number of parameters because you just have a smaller square. And the idea is that you reuse weights when you and apply it to the whole image, but only like a smaller filter that is moved over it. So yeah, parameter sharing will lead to translational invariance. So here's an example. So we have this grid-like structure, and in red we have this convolution filter. And what we do, we weight like every pixel here with some parameter that we have here, and then we move this filter so like to the compute this value here, gives this output, we move it once further, computes this output, and we move it over the whole image till we have it till we have it applied everywhere. And yeah, the main advantage, as I said, is that we share weights between all those applications and those have less parameters. Here's an actual example with some numbers. So here just ones and zeros. So yeah, we can apply this filter like here in the corner, for example, and then we will have 3 plus 9 plus 7 plus 6, which ends up being 25. And then if you move it once further, you will get the next number, 18. So basically, you just multiply the actual value here with what we have in the convolutional filter here. So in CNNs, if you work with this or implement it in TensorFlow or PyTorch, you will come about these terms that are used. There's the stride, which just is how far the filter is moved. Like in the previous example, the stride was just 1, so we always move the filter once further, but you also could move it like 2 pixels or multiple pixels. Then there's padding. Here, the problem that we have also seen this, like here, the initial image is larger, and here it becomes smaller because we don't apply the filter like here, because that would go over the border here. But this has the disadvantage that here at the borders, we only apply this filter. This is kind of in the filter, but only in the filter for this value. whereas this value is multiple times used to compute like a feature map. So what we can do is we can use padding, meaning we put like virtual pixels around the border in order that we can compute this too. There's zero padding where just zeros are put around, or there could be also mirroring where we mirror what's in the image. Then there's pooling. This is an operation used for downsampling. So typically, if we apply the CNN, the convolution part, we typically don't shrink the size of the image, but then there's the idea of max pooling, where we apply some filter to some neighborhood like this, and in max pooling we just pool like the largest, the maximum value, and you just use this in the output. And the idea is that the highest value might be the most important information in this area, and that this way we can reduce like our feature size, which is super useful. And a typical convolutional neural network then would consist of multiple convolutional modules. Like, for example, here we would have one input, then we have a convolutional 2D, which will then give us like same size image, but with the convolutions, a feature image with the convolutions applied everywhere. So, well, we have one convolution which is applied everywhere. Then we do max pooling, which shrinks the size. And then we can have another convolution and do max pooling again. And in the end, so there's now two models, but typical image neural networks nowadays, or the pre-trained networks, have much more convolutional modules. In the end, we will have some fully connected layer on the small states here, smaller state space, and can do some classification or can apply some loss here in the end. This is an example of some convolutional neural network that's is very famous and used a lot, which does like masking and detection at the same time. So we also very useful often in robotics if you have a scene from a camera image and want to like detect objects and find objects. To summarize this part about deep learning, neural networks can represent nonlinear functions, and they are used to like approximate functions when we have input-output pairs given. There can be regularization used to improve the generalizability. We can create deep networks or very deep networks to learn like complex features. So this kind of some black box network. The function is adapted automatically to our training data. And for images, we have seen that convolutions are super helpful because of the parameter sharing. And there can convolutional and fully connected layers can be concatenated as well. And I hope this was a first example on why math is useful and why we can do it, because all these underlying things that neural networks do are things that we have seen in the lecture, like calculating gradients is very important here, gradient descent, and so on. Before I start with the second part, are there any questions?
I have a question about the pooling. And I wanted to ask like how it's done and how like why the output is in this way. The pooling after.
Yeah.
Here. Yeah.
So pooling, as I said, is an operation. So the idea is that we want to make the feature space smaller, and yeah, you apply it in some area, like here you have 2 times 2 in this example, and max pooling, you will just pool the highest value in a neighborhood, which is here the 8. So we have an output of 8 here, and then we move it like to the next part, which is here 5 to 1 6, and here the 6 is the highest number. So here we'll have an output of 6. And like here in the bottom 2 neighborhoods, like this square and this square, there is here a 9 and here a 9. So the output will be a 9 here and a 9 here. And this makes the feature space smaller. There are also other ways like average pooling. Here where you use the average of the numbers. No, this is the max pooling.
Fine, thank you.
Yeah. Okay, yeah, thanks for the question. There are no further questions, so I would continue with the second part, which is some small introduction to trajectory optimization. So in trajectory optimization, we want to find a desired behavior for the dynamical system. So yeah, and this is done by minimizing a performance measure while we satisfy constraints. And so one very standard example here is a dynamical system like a cart pole. So you probably have seen this cart pole example many times before. You have this cart and a pole, and often the task is just to like balance the pole upright. You can apply a force to the cart, and this is your only way to control the system. So you cannot directly control the pole. You can just apply force to the cart, and so you need to swing this around in a way that the pole ends in the upright position here. So a performance measure could be you want to minimize is like you want to minimize the torques that you need to apply, and the constraint that you want to fulfill is that the pole is upright in the end. So you could have this constraint that here the angle of the pole is 0 and going up here. So yeah, that's what we want to do. This trajectory optimization, there are many applications for it in robotics. So I use it a lot in my work as well. For example, you could have motion planning for a pick-and-place robot. You could look into working motion for a humanoid robot. It's also used for quadrotor helicopters. And yeah, the origin comes more from aerospace rockets, calculating trajectories for rockets or satellites. But yeah, it's applied a lot in robotics. So yeah, we have a dynamical system like the cart pole. There are 2 ways we could have described it in continuous time and in discrete time. In continuous time, yeah, the state space, so X is the state space, will be a function of the time, and U are our controls, which also will be a function of the time. And typically in continuous time, then you have here the derivative x dot, so the velocity of the state equals some dynamical system equation here. And yeah, usually this function is given because you can compute it from your system from physics equations. In discrete time, we have discrete time steps. So we usually have a small time step delta t between successive time steps. And yeah, we have a vector x and a vector u. And the system equation is given by the next state can be computed by our systems equation. And usually in discrete time is a bit easier to deal with. And often what is done is that we like use continuous time steps and discretize it by just evaluating it at a small time step delta t to come to discrete time. So if we now have such optimal control problems, so we want to, let's stick with our card pole example, we want to have this pole balanced upright. Then we have like this state B here, which will be like the pole in the balanced upright position. And a global method now, like everywhere would everywhere in the state space would be defined. So everywhere, no matter where you are in the state space, you would know what actions you would need to do in order to end up in the end in this closed loop solution. And yeah, typically this is, can, for example, be done by dynamic programming. But yeah, if you know about like the dynamic program, you also know that this does not scale well to very high dimensions, and in the continuous cases is even hard to apply, more difficult to compute. Trajectory optimization is a local method, so we are only interested in one start space where we are, and we're just interested in the trajectory, how we end up in this goal state B. And yeah, we also only then compute one trajectory and only know here what we need to do. And yeah, it's a simpler problem because we don't need to know it everywhere, so it should be less difficult to compute. And also it scales better to a higher dimension. Makes sense because also we need just one trajectory and not like a solution for everywhere. Let's jump into the basic formulation. So we want to minimize our controls U. So the decision variable is our controls U. We want to minimize our performance measure L in a given trajectory, so a given time frame, capital T, like is then the time horizon. We want to subject this to the following things. So we want to subject this that our dynamics equation, our dynamic system equation is still fulfilled. We have a start, an initial condition where we start at, and we have additional constraints that come from our task, like we want the pole to be balanced upright. And yeah, so L is the performance measure. Could be like minimizing accelerations, torques, or other costs that are assigned with the states or controls. Now this was for the continuous case, and yeah, we want to convert this into some parameter optimization problem. So the problem here is that this is a function, so minimizing finding a function here is a bit untractable. So we need to parameterize it somehow so that we have a parameter optimization problem. And yeah, this is also often discretization, what we refer to. And there are different methods possible, like the direct method, the shooting method, collocation method, and I will talk about this in a second. So this is for, we have a continuous time problem and we want to convert this into some parameter optimization problem. If we like start from the beginning with some discrete systems equation, we don't have this transcription step. But yeah, so for direct shooting is a very simple method. We just discretize the continuous problem by a small time step, delta t, as I said before. Now we only have u as our decision variables. And why we only have u is because we roll out the dynamics. So we have this now a discrete dynamics function. And we can compute the next state by using the previous state and the previous controls. And yeah, we're still subject to a start state and additional constraints. And now we have a minimization problem, a nonlinear minimization problem. And we have nonlinear dynamics where like we have here a sum, and here we have this this xt and which is rolled out. So you need to think about this as you just compute this multiple times by inserting like the state into the function like multiple times, and in the end you will have some long chain of functions here, which has the disadvantage that if you want to compute the gradient, we need to go through this whole chain. Opposed to this, there's also the direct transcription method. Here we have u and x as decision variables in our minimization problem. And this makes this simpler here. So here we don't need to use the system equation to compute the new x, because it's, we can change, it's a decision variable, we can change it, but we need to add a constraint that our system equation still holds. So to compare again, here we don't have this constraint. We had just we just compute it here, so it's like implicitly fulfilled. We just have u here. For the transcription, we have u and x here. We have explicit constraints of the system, constraint of the system equation, but we don't need to compute this using rolling out the dynamics. So when comparing these two methods, direct shooting has less decision variables because the state is not added, but it might suffer from that the gradients are a bit less well conditioned, because we chain this together, and then if we have like complicated dynamics and maybe large matrix multiplications, then the gradients could vanish in the end. And also the use in the beginning influence the whole trajectory, so they might have more influence, which also might not be desired. Direct transcription, on the other hand, does not have those problems, but instead it has more decision variables and more constraints, which also made it harder to in the end optimize. But also one advantage is that it can be easier parallelized, because all the constraints could be computed in parallel, and we don't depend on computing from to another time step in order to compute one of the constraints for the dynamics. So So direct shooting is often used when we have a good initial condition of the problem. Direct transcription. If you don't have a good initialization, it might work better, but in the end, one has to try on the specific problem to see what works better. And of course, like those are like two sides of the end. There are also combinations of both possible. One could have like a constraint like this, only at specific time steps, and use shooting in between. Then there are other more methods like direct collocation. For direct collocation, one does not discretize with the small time step, and instead one wants to approximate our function with polynomial splines. And this has the advantage that everything is, that you can evaluate your function everywhere. And you then usually just add constraints at for like start and end of the spline and for not points, and optimize in a way that you optimize for splines. That's, don't want to go into too much detail here. If you're interested in this, you can look up this source here, an introduction to trajectory optimization, how to do your own direct collocation. There's also a video on YouTube about this. Then I talked a lot about additional constraints that could be used, and their trajectory optimization is very flexible. There are many different constraints possible. It just needs to be differentiable in order that we in the end can use gradient-based optimization to find our trajectory. Examples would be from robotics here would be like we could have joint limits for the robot. We could want some robot end effector at some position P, where we would use some forward kinematics map to get the end effector position from some states, and then subtract the position P, and want to add an equality constraint. Or we could have a robot end effector that should be out of collision. Usually desirable to find trajectories where the end effector is out of collision, or where the trajectory is out of collision. And there we could have inequality constraints with some signed distance field. In order to solve the NLP, there are many solvers possible. And I don't want to talk much about this because in lecture 10, you had optimization and also constraint optimization, so you could also take a look there. And how to initialize. If you have a problem and don't know how you want to initialize your trajectory, it's typically you could use like very simple initialization, like you say all your torques are 0 already, so all your controls are 0 already, so that your costs are like at the minimal point. Or you could neglect dynamics and remove difficult constraints, solve some easier problem, and use this as an initialization. To summarize, trajectory optimization is a powerful tool for solving an optimal control problem, and it's very flexible, so there are many ways to formulate constraints, many different possibilities. But it is a local method, so it only finds some local solution. And also different initialization due to the nonlinearity of the problem often leads to different solutions in the end. Okay, thanks for listening. So that was the second part about trajectory optimization. Are there any questions about trajectory optimization?
Excuse me, I have a question about the direct shooting. Uh, why we say like the gradient is less well conditioned?
So if you look into this equation, you have xt here, and you need this t comes from like the sum, so you need it at every time step. So when you start at some initial x0, or let's formulate it this way: if you want to have, so you start with x0, you have all your controls given because you optimize over them. But to compute like the last state, the state in the end of the trajectory, you need to apply like all the controls. So you only have your start state, and you compute your next state by applying your controls. Then you get your next state, and then you apply your controls again. So you chain this, you have a concatenation of many of this nonlinear system dynamic functions. And the problem when you now take the gradient with respect to u is that you need to compute the gradient through the whole chain. And this might be less well conditioned because, this dynamics here, this function f might be nonlinear, might include matrix multiplications. And if you chain a lot of them and need the gradients through the whole chain, you might suffer from numerical problems and things like this. Clear?
Clear, thank you.
You're welcome. Okay. So the next part would be by my colleague Yuchen. Okay, then I will. So I assume you share your screen, so I will stop sharing and hand over to Yuchen. Yuchen, I think you're muted. So yeah, Yuchen had some microphone issues, so she will rejoin in a second, and then we will continue. It's still not working. Eugen, it looks like you're muted in WebEx at the moment.
Okay, now does it work?
Now,
Okay.
now it's good, yes.
Yeah, the first one I think was because something was wrong with WebEx, and then now I forgot to unmute.
Yeah.
Sorry.
Okay, then yeah, I will let you present your slides.
Okay. So, hi everyone, my name is Eugen, and I'll be introducing you guys to natural gradients. So let's first start with gradient descent. So we have a problem where we want to find a local minima, or optimistically a global minima, to a function. And this function can be some function that maps a multi-dimension to a single number. For instance, like the potential function or a cost function in a robotics problem, etc. And the way we find the local minima or the optimal minima is that when we assume this function is differentiable, we can take steps in the direction of the negative gradient. And that's what the gradient descent is. So we take small steps in the direction with the size of the gradient of its function. So when we have a quadratic function, let's say we start from this position, and here we have a big gradient, so we take a big step, and then a smaller gradient, smaller, 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 and when you reach at almost at the local minima, then you take very little steps to converge to the optimum, the global minima of a quadratic function. And this can be a problem because when you have a big gradient here, it means that you can take big steps. And when you have a smaller gradient, then you're taking smaller steps, which takes longer to converge. So this would be the limitations of the gradient descent, where when you take the gradient of a function as the step, then depending on the size of the gradient, you might be actually converging very slow or might not be able to converge at all. For instance, when you are at this position and you take the gradient, this gradient would be really big, so it leads to some point over here. And you take another gradient, and when you have a large gradient, you might not be able to converge. It can oscillate between these 2 points and never reach the global minima. Or for instance, when you have a very small gradient, you would take very small steps, and it would take a long time to actually reach the global minima. So the gradient itself would give a good direction, but not the good step size. And the simplest way then to do is to normalize this gradient, the size of the gradient, and we rely only on the alpha, the step size, to take small steps towards the global minima. So this problem is exacerbated when you have a function not in a Euclidean space, but some other space, a multi-dimensional space. For instance, let's say we have a map and we want to find the shortest distance that will take us from, say, Boston to Korea. In a 2D map that's mapped over a Euclidean space, the shortest distance would then to be from Boston to Korea, a straight line. And it will go across the Atlantic Ocean to Europe, to Central Asia, and then to Korea. But actually, the shortest distance from Boston to Korea would be to fly over the North Pole, closer to North Pole, because the world itself is mapped over a sphere. So there would be a big difference between finding the distance in the 2D Euclidean space and considering the actual manifold of the space. And this is where natural gradient comes into place. So when you take gradient steps, you modify the direction according to the Riemannian structure of a manifold. And we use a Riemannian metric tensor that characterizes the intrinsic curvature of a particular manifold in an n-dimensional space. So coming back to our function, if this function f, the state x, was mapped over a Euclidean space, it wouldn't be such a problem. But if this function, let's say, is a probability distribution function of a neural network, or this function could be a cost function that is over a space of a 7-dimensional robot arm, then this manifold itself would be n-dimensional, and there would be a difference between when you map it to a 2-dimensional Euclidean space. So that's where we use this natural gradient to modify the search direction to take the gradient steps. Okay, so when we derive the gradient step function, we first start with an optimization problem. So we are trying to find the parameters that minimizes this function, f. And this function, we set it as an optimization problem where we find the parameters that minimize the linear approximation of this original function. So we find the parameters that minimize this linear approximation, subject to that we take small steps towards the next parameter. And we can solve this problem using the Lagrange multipliers. So if we express it with the Lagrange multipliers, it would be like this, with the Lagrange multipliers in the step. And when we take the gradient, the first order gradient of the Lagrange, this equation would then lead us to the step update function. So this would be the gradient descent update rule, where we have the parameters, and the next parameters would be from the current parameters taking into the direction of the gradient with some weighted norm. And so this is the gradient descent update rule. And when this A is generalized A weighted norm is defined as a quadratic, and it plays a significant role in defining the search direction. So when we first saw the gradient descent, this A would be a identity, which means that for every dimension, you're stretching in the same amount in both x and y. And this could be a problem because if you have a gradient that's really big towards x direction, a steep gradient towards x direction, and a very flat gradient towards the y direction, then if you take the same step, then in the x direction, you would be taking a very big step, whereas in the y direction, you would be taking a very small step. So the problem occurs when we take a stateless descent. To alleviate this, then we can take into account now the Hessian. So the Hessian would express the second order, the curvature of the actual manifold in the Euclidean space. And this is what the Newton method does. So it looks into the Hessian, the second order curvature of the Euclidean space, and let's say that, oh, here it's very steep, so you take a smaller step. If it's very flat, then you take a bigger step. And the gradient, then the search is modified based on the Hessian. So similar to this, what the natural gradient descent does, then it looks into this Riemannian, what is called a Riemannian metric tensor. And this Riemannian metric tensor then characterizes this intrinsic curvature, similar to what the Hessian does for the Newton method, but instead of the Euclidean space curvature, it looks into the n-dimensional dimensional space, the curvature of the n-dimensional space manifold. And that is what we call a natural gradient descent. So comparison to using the gradient descent, the natural gradient descent will then lead to faster convergence, but because it takes into account the natural shape of the manifold that it has for its function f. So if you look at gradient descent, what you would have is you would take the steps in the direction of more or less perpendicular to the gradients. So here you would be lucky enough to go directly into the global minima, but in this case, you would first have to travel this way, and then where here it's really flat, then we'll take small steps towards the global minima. Whereas the natural gradient descent takes into account the intrinsic shape of this underlying function. So from wherever you start, you will more or less reach the global minima faster than the gradient descent. Okay, and we'll now then discuss about the Fisher information matrix. So this f function that we discussed, if this f function is a function over the space of probability distributions, for instance, let's say we have a policy distribution of a robot arm, then you want to find the parameters that lead us to the cost function, or the probability of a policy. Then this G, the Ramanan metric, would then be called a Fisher information matrix. It's called when the space lies in the probability distributions. Okay, so then how do we measure the distance in the distribution space? Because we're taking this small step. So in order to compute what it means to be a small step in a distribution space, that's when we use the KL divergence. So the KL divergence is, strictly speaking, is not a distance metric, because KL divergence of two distributions is different when you do one and the other, and the other one and KL divergence of distribution A and B, and KL divergence of distribution B and A. But it still is a measure to measure how close two distributions are, and it can be asymptomatically symmetric when it's really, really close in the local neighborhood. So this KL divergence is a measure to measure how close a distribution is to another distribution, and when we're concerned about how the output distribution changes based on the prior distribution. So the natural gradient updates can be used with the Fisher information matrix as distance measure. Okay, so this Fisher information matrix defines the local curvature of the distribution space, for which the KL divergence is the metric. Similarly, when we use the Newton steps, the Hessian express the local curvature in the Euclidean space. And this KL divergence can be approximated as a norm, a weighted norm with the Fisher information matrix, weighted by the Fisher information matrix. So coming back to our optimization problem, where we want to find the parameters that minimize this function f when this function is a probability distribution function, then we can express it as minimizing this first order linear approximation of a function, subject to that we take small steps in the distribution space. And how do we measure that in the distribution space? That would be the KL divergence. And similar to what we do for gradient descent, we can solve the problem by using Lagrange multipliers, where here this KL divergence will be replaced by the weighted norm using the Fisher information matrix. And similar to what we did for the gradient descent, we can set the gradient to 0 and solving it for the delta parameters, the delta pi, the delta thetas, then we can have the natural gradient, what is defined in the equation. So what this Fisher information matrix does is it looks into the probability distribution space, and when you take a gradient step, it looks into whether how much in one dimension you should stretch, or in another dimension you should not stretch. So for each dimension, you can take different sizes of steps for the gradient update rule. And this is widely used in the robotics field, where, for instance, you have a neural network in machine learning, and where you have a distribution that you want to infer, and you want to modify the parameters of the distribution, then you can have one distribution and another distribution, and you tweak it such that using the Fisher information matrix, that you tweak it into the direction of the probability distribution, similar to variational inference, and also in reinforcement learning, such as natural ethnic critic or trust region policy, is basically in trust region policy, you have a neural network or a policy distribution, and you say what is called a trust region is that you take a small step that is measured by the KL divergence, and that is also expressed by the Fisher information matrix. So you don't take a big step into changing the parameters of a probability distribution. You would have a trust region, but you don't take such a big step into changing the parameters of your probability distribution. So yeah, that's basically basic introduction about natural gradients. So this natural gradient descent takes into account the underlying geometry of the n-dimensional space, which may not necessarily be Euclidean. And for the natural gradient descent, we use KL divergence to measure the closeness of two distributions. And Fisher information matrix is what you use to define this local curvature of the distribution space. And using this Fisher information space, you can either stretch or squish along a particular dimension when you take a step in the gradient for the gradient update rule. Yeah, so that's it about natural gradients. Do I have any questions? Do you guys have any questions? Okay, if not, then I will then pass it over to Philip or Jim. I'll stop sharing.
Yes, thanks, Yuchen, for the presentation. This now was the first part of this lecture session today. So now we will have Q&A, so you can ask questions about lecture slides or about the exam. So just feel free to ask anything. I think Jim wants to join as well, so I don't know whether he's already here. But yeah, let's just start. So if you have any questions, you feel free to ask them or write it in the chat. Hi, Jim.
So I think that I think I said this at several points during the lectures, hopefully. Our department is going to close temporarily until they find a new professor, which should probably happen this year, but probably not next semester. It's not really clear when. So and anyways, when the new professor is going to start this course, this theoretical and methodological foundations of autonomous system is going to be mapped to a different kind of course, which will probably have to do with like the necessary background for a mathematical background for machine learning, but it's not really clear yet. So the way that we are kind of trying to ensure that you have sufficient possibilities for exams is that we have an exam. Our exam is quite early. It's mid-February, I think, so in only a few weeks, 2 or 3 weeks.
Yeah, it's the 18th of February.
Mm-hmm. And we might have a second possibility before the end of the semester, depending on the number of people who fail this exam, and and that would be in March. So I want to stress that you might not have other possibilities to pass the exam after March. So you should be aware of that and try to give your best to finish this topic by the end of March. If you don't, then I think it will be probably remapped to something like the mathematical background for machine learning or something like that. And the content will be slightly different. And so I think it's worth it if you invested time in this lecture to try to pass the exam by the end of this semester. Another thing I wanted to announce is that there will be a follow-up for reinforcement learning. So that's clear now. And the content, I think, would be quite similar to what we used to do. And this would be starting in April or May, or whenever is the start of the second semester. April. I don't know. Do you have any questions? So I had the question in class. I answered this. Is there any sample of previous exams? No. So we haven't done that in the past, and I don't think it would be fair to start doing this now. Okay. Okay, the other things were. I got the question whether it was an open or closed book exam. It's a closed book exam. So the exercises that we give are not very hard. They are, I think, easier than the exercises that you got in the exercise lectures. But you need to know the formulas and
Sir, I wanted to ask if the exam will be online or in presence.
there was never any online exams.
Okay.
So yeah.
And
I mean, we have like the university has COVID concepts for exams where you have enough distances. Yeah.
okay. And we can know also like which will be like the main topics that we have to focus more, or it's like all the same.
I think it's very important that you lock down the vector calculus things because it's kind of crucial for understanding everything else. I mean, and you need to understand kind of linear algebra for some of this stuff. So I would say like the vector calculus thing is the most important topic in the sense that it pulls on linear algebra and it pushes on optimization and these kinds of things. The lesser important topic, I would say, is maybe differential equations. But the two lectures that we have on differentiable manifolds, so Lie groups and differential geometry, I would kind of want to understand these lectures as they also kind of tie with vector calculus, like give you like a lot of examples of how vector calculus ends up being implemented in kind of like more concrete mathematical concepts. And yeah. Linear algebra, I think you've all seen it before. So I mean, you have to know the axioms of vector spaces, groups, and everything. I mean, this is really kind of supposed originally to be more like a recap, you know, of what you have done in your bachelor's or something. But it's also then also very important. I think for the different, that's okay. So we need to memorize formulas and equations, or they would. So that's the for Mohammed. When I say I think so. Solving exercises is enough to pass the exam. The exam is about solving exercises, not so much about spitting formulas. But you might need the formulas, some formulas to solve the exam. So you need to memorize some formulas, yes. Like as I said, like in the vector calculus lectures, we introduce things like the Taylor expansion, things like these Maclaurin series, things like that. What is like the shape of the Hessian matrix? These formulas you need to, or the Jacobian, these formulas you need to lock down and know. And I think if you want to use some book exercises, I mean, we are following, I think for 3/4 of the lectures, we are following the mathematics for machine learning book. And I think I put it everywhere in the slides. And this book has a bunch of exercises. So you should there have a lot of kind of material where you can test yourself. If you want to practice some exercises, there are many there on top of the ones that you had in the tutorials. I think that's good. Will there be programming questions in the exam? Did we ever do this, Philip?
Typically, I don't think that we have ever that you need to write down some code or something. We don't have this. There might be that you need to give in pseudocode style something, but I don't think we have planned this, right?
Yeah, we might have some pseudocode maxim. I mean, we're not gonna force you to write Python code or something like that in the text now.
Yeah.
Maybe if we ask for pseudocode and you want to write in Python, it's also fine. But I mean, the only algorithms that we saw in the end were in the optimization lectures, right? So if there's some pseudocode coming out, you know where it's going to come from, right? Yes, the problems in the exam are similar to the ones in the exercises. Though it's not like we change the numbers and we give you the same exercise, right? They are a little bit different. One thing that you might want to also focus on is the rules for in vector calculus. You know, there are some kind of algebraic rules for applying the rules of differentiations to kind of vector valued functions. And I think those are important. So you want to maybe do a few exercises where you find exercises of those that calculate what is the Jacobian of that equation or the gradient of that equation or whatever by applying vector calculus rules. And you want to be kind of familiar with those because we might have exercises on that. And if you know you're not maybe too fast at doing those, you might lose time there. Yeah, so the problem with the differential manifolds and the Lie group topic is that it's usually a little bit more advanced than the way that we treat it. So I don't have any book where I can point you to, and there will be exercises at the level, I would say where the level is low, like what we will ask. Usually the exercises that you would find on Lie groups and differentiable manifolds would be a little bit more advanced, and we're not going to go into that. So I think you should just log down on the class, so the slides, and then the exercises, and that should be enough. And as mentioned, I think those topics are more for you to kind of get the picture of how vector calculus kind of moves on to complicated mathematical concepts and how it's being implemented. Like we saw many examples of Lie groups and differentiable manifold. Like the first one of those would be the general linear group of matrices. There's a whole book on the general linear general linear group of matrices and how to optimize in this group. The idea is like you're looking for matrices that are invertible, and you have some kind of objective function, and you're using optimization to find optimal matrices that solve a particular problem. And because of the geometry of the general linear group, then it's what Eugene was explaining in her topic here, that the geometry of the underlying space in which you're looking or searching, so the one you're optimizing, really is important in the optimization algorithm that you design, right? So I think it's more like to give you this concrete topic that ties things together, and that I think is very important for if you move towards like computer graphics, machine learning, robotics, these things. It's important to understand them. But we're not going to have very difficult exercises on these two topics. I think they are more like to give you the content, but I don't want to test you too hard on these topics. As I said, vector calculus and linear algebra, and then eventually optimization, this is going to be like the thing that I really want to test you on. Of course, there will be some questions on differentiable manifolds, maybe on the algebra, but they will be more like these bonus points, or to really get a good grade. Okay, so I think if I answered all the questions that you might have, we're going to close it. How do we do this usually? Do we, Philippe, do we give more points than needed for 1.0?
Yes. So I think usually you need 40% of the points to pass the exam and like 90 to get a 1.0.
So there is this 10% bonus thing, and in my mind, these 10% will be these differentiable geometry topics. A calculator is allowed?
No, calculator is not allowed. I think we don't have any auxiliary material. So only pen and paper.
Okay, so we hopefully recorded this session, and yeah, so if anybody's asking, we should be...
Question about the probability. There was some exercise, and there, like, I used the MATLAB to do calculus to compute, I don't know, the variance or covariance. So I suppose since we don't have a calculator, we don't need to do this calculation, right?
Yeah, we will not have exercises that that force you to use some kind of calculator or MATLAB or whatever. If there are some calculations numerically, it will just be a few fractions or some sums or products, easy things that you can do by hand. Or actually,
Okay. Thank you.
right on the top of your head. Yeah. Okay, so yeah, as I said, the lecture is, this session is hopefully recorded and will be pushed to Ilias. So if some people could not attend, or if you want to watch it a second time, it will be there. And yeah, I wish you luck for the exam. And again, you know, March will be kind of the last thing if you want to be tested on this topic, and if otherwise you might have to kind of go through another similar content that will, but there's no clarity about what this will exactly be yet. So, okay, good luck.
Yes, just for the last question, there will be no lecture next week and also no tutorials next week, but this week, Thursday, we will have the discussion of the last tutorial.
Yeah, be careful with the points for the shine. So this week is the last opportunity to validate the thing, right?
Yeah.
So you should really do that if you haven't already have the check for the exam. Ciao, good luck.
Bye-bye.